Now what if, instead of applying our impulse at 2 pi, we apply it at 5/2 pi? Now that's 2 pi plus 1/2 pi, which means we're 90 degrees out of phase with this thing. Okay, that means that right here, t is 5 pi over 2. Well, we're not going to go through the solution, but everything in the solution remains the same, except that you're going to have a minus 5 pi over 2 times s here, which means you're going to shift the thing 5 pi over 2 units to the right. So what you're going to have is, well, your solution, and it should be obvious. If not, write it out and then ask yourself why it should have been obvious. We're going to get y. I don't want to write it there. I'm going to need that for my graph. Move over a little bit to the left. Shift my writing over to the left. Not sure what that does to the symbols, but we'll just write it. Okay, y equals sine t plus a sine of t minus 5 pi over 2u of t minus 5 pi over 2. And I'm still kind of getting in my own way, but I think I can deal with it. Okay, well, what have you got now? That might be a little small to read, but you know, we're just shifting. These are 5 pi over 2's here, which means now that our Heaviside function times the sine of the shifted argument is going to be 0 all the way up to 5 pi over 2, and then it's going to follow a sine curve from there. Except now it's sine of t minus 5 pi over 2, so it's never mind. Yeah, for a minute there I thought I'd looked at it wrong earlier, but that was only an illusion. Okay, so we have something that looks like this. Okay, and of course this dotted line. Okay, the dotted white line represents the continuation of the original oscillation, but that now has to be superimposed on the, I call it the Heaviside function, but the multiple of the Heaviside function. I'm not even sure what to call that, but it's the response to the unit impulse. This is the response curve. Okay, well, we add these two, starting at this point, so this thing immediately starts up with the same slope that this one starts up with. However, this thing rapidly decreases as this one increases in such a way that when you get to this time, this function is 0, so that added to this function, it just gives you whatever this function is, and we get a curve that, at least for right now, looks like this. Then this curve is steep downward. The white curve is steep downward. If the original oscillation had continued, you'd have your maximum negative velocity at this point. And this thing is pretty level, so it's going to start downward with the same slope as the white graph. But then, by the time you get down here, this graph is 0, and this graph is at its minimum. So we're going to just come on down to a minimum at this point. And then, it's not going to be a minimum at this point. That was foolish. Excuse me. Quick correction. If I'd have sprayed the cloth instead of my thumb, it would have been quicker. Okay, my picture's getting a little messed up here, and I do apologize. By the time you get down here, it's going to behave just like this one. So it's still going to be pretty steep when it gets down here. It's going to wiggle down a little below this one. It's going to come back up and join this one at its negative peak. And then it's going to come back up. By the time you get here, it's going to match this one, so it's going to come back up like so. And it's going to start the cycle all over. Okay, now I didn't draw that exactly right. It probably doesn't go up quite as high as this one makes it look, although maybe. Okay, anyhow, what you're doing now is you're starting a new cycle. And it's not in phase with the old cycle. Okay, it's got a little more amplitude, and it doesn't peak, and it doesn't cross the x-axis at the same points that the original sine function would. Okay, so you have a phase shift and an amplitude change. And I should have used, to be consistent with that picture, should have used purple here. So let me just trace this thing over. Make it look at least halfway purple. Okay, so this green-purple graph is this plus this. Okay, well the green-purple graph then is basically sine of t plus a sine of t minus pi over 2. Why pi over 2 when I had 5 pi over 2 here? Because of the periodicity. The sine function has a period of 2 pi, so I can add or subtract any multiple of 2 pi to the phase and I still get the same thing. Okay, so the purple phase of the curve follows this. Now you can use your basic trigonometric identities for the sine and cosine. Sine of t minus pi over 2 is what? Some combination of sines and cosines of t and pi over 2 along with this, and then you can combine them into one function, which might be a sine of t minus phi, where the phi looks to be maybe pi over 4. Okay, because these have equal amplitude. You have this, I suspect pi over 4. I haven't done that. I'm not going to do that. That's trigonometry. That's pre-calculus level. But you need to be able to apply the trigonometry to do that and discover this, and then see if it's compatible with your picture. We're superposing the solution we get for the Dirac delta with the solution we get for the undisturbed system. Now there are other combinations we could do. We could now think of applying the delta force, the impulse, applying the impulse at any time. And we could even, apply a bigger or lesser impulse. If your applied force was a 2-unit impulse, then, of course, this green graph would have twice the amplitude, and you'd have a much bigger distortion of the original oscillation. And you want to think about that. You want to be able to picture these things. You also want to be able to do the pre-calculus and manipulate the trigonometric functions. Personally, I don't remember any formulas. I just start with Euler's identity and rederive them because I don't do them that often. That's not why I'm not doing this. I could have done that in advance, had those formulas in my head. But I just, I'm not going to burden you with this because this is something you need to review if you don't know how to do it. Okay, so you see that we can get a picture of any oscillation superposed on any solution to the applied problem. And we can even solve the basic homogeneous system, okay, which is all this is a homogeneous system with initial conditions. But we solve the original homogeneous solution using just standard methods if we don't want to bother with the Laplace transform. All the Laplace transforms are very easy here. And then we can superpose the solution to just what happens if we have the delta function, okay? Not sure you'd want to do that, but you could. You can think through how that would be. Okay, so there's another example, just another example, and I'm just going to draw it. If we start with the oscillator at its positive maximum position and apply an impulse resulting in a Heaviside function that looks like this. No, I don't want to do that. Okay, I want to do this. And I want to be careful, so I want to keep this in the right phase. You can see, first of all, you can estimate. I'm applying the impulse just shy of the 3 pi instant. So, you know, maybe 3 pi is about 9.5. So maybe I apply this at 9 or a little less. T equals 9. And I apply a positive impulse. Well, then what's happening? I'm applying a positive impulse, because this thing is positive, to a pendulum that's in negative motion. So the pendulum's going to collide with the impulsive force, and you're going to have a decrease in the amplitude. And if you combine these two graphs, you see that you have a decrease in the amplitude. It looks like the amplitude is probably going to maximize around here. It's going to come up to here. Actually, it's not going to come up to here. It's going to come up to about here. So it's going to maybe come up to here and down to here, and so forth. And I'm not necessarily drawing that in the right phase. You can think about how that works. Okay? So there we have it. Let me make one more observation. In any of these cases, your denominator is always going to be this factor of your Laplace transform. So it's always, it's always going to be a sine function. Okay, it's always going to be a shifted sine function, and it's going to have the same period because you're going to have a sine of t because you have a 1 here. Of course, if you want a sine of 5t, then it'd be s squared plus 25, and you'd have a 25 over here, and so forth. So again, these functions are going to have the same period in any case where you do this sort of thing. Okay. So the periods of these functions are going to be equal.